Radio waves. Cosmic radiation comes in three broad families: electromagnetic light, fast-moving particles, and ripples in space-time itself. The largest family by far is electromagnetic, a single spectrum of light running from low energy to high, and its lowest energy member is the radio wave. Radio waves are the longest wavelength form of light in the universe, with individual waves that can stretch from centimeters to kilometers. Across the cosmos, they pour out of spinning neutron stars, the jets of distant quasars, and vast clouds of hydrogen gas humming at a specific radio frequency. Because their wavelengths are so long, they slip straight through the dust that blocks ordinary light, revealing regions of space that are otherwise completely hidden. Radio was the first invisible form of cosmic radiation humans ever detected. Microwaves. Microwaves sit just beyond radio waves, with slightly shorter wavelengths, and in space they trace some of the coldest material there is. They are emitted by frigid clouds of gas and dust, the very nurseries where stars are born, at temperatures only a few tens of degrees above absolute zero. Mapping the cosmos in microwaves lets astronomers find and weigh these cold, dark clouds long before any star ignites inside them. But the most important source of cosmic microwaves is not any single object. It is a faint glow that comes from every direction in the sky at once, the oldest signal in existence. The cosmic microwave background. The cosmic microwave background is not a separate kind of radiation, but the single most important source of microwaves in the sky, and the oldest light in the universe, the afterglow of the Big Bang itself. It was released about 380,000 years after the beginning, at the moment the cooling universe first became transparent and let light travel freely. Back then it was a brilliant glow, but over 13.8 billion years, the expansion of space has stretched that light all the way down into microwaves, chilling it to just 2.7 degrees above absolute zero. It fills all of space and arrives from every direction at once. Its almost imperceptible ripples are the seeds from which every galaxy eventually grew, making it a baby picture of the entire cosmos. Infrared. Infrared is the radiation of heat, with wavelengths just longer than the reddest light our eyes can see. Anything warm glows in it, from a human body to a forming planet, which makes infrared one of the most revealing bands in all of astronomy. Crucially, it passes through cosmic dust that blocks visible light, so infrared telescopes can peer directly into the hearts of dusty stellar nurseries and watch stars and planets being born. It also captures the faint warmth of the coolest stars and the light of the most distant galaxies, whose visible glow has been stretched into the infrared by the expansion of the universe. Visible light. Visible light is the thin band of radiation the human eye evolved to see, and for almost all of history, it was the only window we had onto the universe. It sits in the middle of the spectrum, and it is the range in which stars like our sun shine most brightly, which is no coincidence. Our eyes are tuned to the light our star produces most. Glowing nebulae, reflecting planets, and billions of stars all pour out visible light. It passes easily through Earth's atmosphere, which is why we can see the stars at all with the naked eye. Ultraviolet. Ultraviolet radiation carries more energy than visible light, and in space it is the signature of things that are hot and young. It streams from massive newborn stars, from the scorching surfaces of white dwarfs, and from the turbulent cores of active galaxies. Ultraviolet light is powerful enough to strip electrons from atoms, which is exactly what makes vast clouds of gas glow as emission nebulae. On Earth, we are shielded from most of it by the ozone layer, and that protection is essential because the same energy that lights up nebulae is the energy that causes sunburn and damages living cells. X-rays. X-rays are high-energy radiation produced by matter at extreme temperatures, often millions of degrees. In space, they mark the most violent and superheated environments there are: gas spiraling into a black hole, the surfaces of neutron stars, the debris of exploded stars, and the thin, blisteringly hot gas that fills entire galaxy clusters. Where visible light shows a calm night sky, X-rays reveal a universe seething with energy. They cannot penetrate Earth's atmosphere, which shields us, but also means every cosmic X-ray must be captured by telescopes launched into space, high above the air that blocks them. Gamma rays. Gamma rays are the highest energy radiation in the universe, with a single gamma-ray photon carrying up to billions of times the energy of a photon of visible light. They are born only in the most extreme events known: exploding stars, colliding neutron stars, matter meeting antimatter, and the titanic bursts that briefly outshine entire galaxies. A gamma-ray burst can release more energy in seconds than the sun will produce in its entire lifetime. This radiation is so penetrating and so violent that only the most cataclysmic processes in existence can create it, making the gamma-ray sky a map of the universe at its most destructive. Cosmic rays. Cosmic rays are not light at all, but actual particles, the nuclei of atoms, mostly protons, hurled through space at very nearly the speed of light. They are flung outward by supernova shockwaves and the jets of black holes, and the most energetic ones come from sources still unknown. When they strike Earth's atmosphere, they shatter into showers of secondary particles that rain down constantly, passing harmlessly through your body several times a second. The most powerful cosmic ray ever recorded, nicknamed the Oh My God particle, carried the energy of a fast-pitched baseball packed into a single subatomic particle. Solar radiation. The sun is not only a source of light, but a source of high-energy particle radiation. During solar flares and violent eruptions, it hurls out sudden storms of charged particles, mostly protons accelerated to enormous speeds, in bursts known as solar energetic particles. This is a genuine radiation hazard. A powerful solar storm can endanger astronauts beyond Earth's protection, damage satellites, and disrupt power grids on the ground. The same particle streams, funneled by Earth's magnetic field toward the poles, set the sky ablaze as the auroras. Every star flares and storms as it burns, flooding the space around it with bursts of fast-moving particle radiation. Neutrinos. Neutrinos are among the strangest forms of cosmic radiation. Ghostly particles with almost no mass and no electric charge, which barely interact with anything at all. They are produced in staggering numbers by the fusion in the sun's core, by supernovae, and by the Big Bang itself. Trillions of them are passing through your body every second, and nearly all of them sail straight through the entire Earth without touching a single atom. Because they escape directly from the hearts of stars and explosions, catching even a few of them lets astronomers see inside places no light could ever escape from. Gravitational waves. Gravitational waves are radiation of a completely different kind. Not light, not particles, but ripples in the fabric of space-time itself. They are created when massive objects accelerate violently, above all, when two black holes or neutron stars spiral together and merge. Predicted by Einstein a century ago, they were finally detected in 2015, when instruments on Earth felt a wave from two black holes that had collided over 1 billion light-years away. The waves stretched and squeezed space by less than the width of a proton. They let us sense events that give off no light at all, listening to the universe rather than watching it. Hawking radiation. Hawking radiation is the most exotic radiation of all, and it means that black holes are not entirely black. Predicted by Stephen Hawking, it arises from the strange behavior of quantum particles right at the edge of a black hole's event horizon, causing the black hole to leak a faint trickle of energy into space. Over unimaginable spans of time, this slow bleed causes the black hole to lose mass and eventually evaporate away completely. It has never been observed, because for any real black hole, the glow is far too faint to detect. But if the theory holds, then even the darkest objects in the universe are quietly shining. Thanks for watching. Which type of radiation is the hardest to wrap your head around? Drop it in the comments. Also, please remember to like and subscribe if you enjoyed this video.